All right, so we finished up the video where I left you guys with this problem right here, and I asked you to use the cover-up method to basically figure out what your A and what your B was going to be. So once you do this, you should end up with 2 minus 2, and then once you've integrated all of this, you will get x cubed plus 3x. Forgot the plus sign right there. So plus, take out the 2, ln of x plus 1, minus, take out the 2, ln of x minus 1, and since du for this part is just going to be 1, we don't have to worry about it, and that's a plus c. Now, like I told you guys in class today that the College Board and the AP exam, if this was a multiple choice question, they will actually simplify this a lot further. So we notice here that both of these have a common factor of 2. So this, you could take out the 2 from both. And then what do you notice? Is that this right here, you can use the property of log, the quotient property of logs, because you have 2 logs with the common base, and they are being subtracted. So this is actually x cubed plus 3x plus 2, and then in here this becomes ln of x plus 1 over x minus 1, absolute value, plus c. And then the last thing is, they could take this 2 and turn it into an exponent for this whole entire thing. Okay, so this becomes x cubed plus 3x plus ln of x plus 1 over x minus 1, and all of this is going to be squared. And you notice that I got rid of the absolute value signs, and the reason why is because they're going to be squared. So no matter what ends up here, once you square a number, it's always going to be positive. If it's a negative, it's going to be positive. If it's positive, it's going to be positive. So this right here would actually be the multiple choice answer on the AP exam. All right, which brings us to the next thing. So this is why we learn partial fractions. The whole reason why we learn partial fractions is that so we are able to solve this differential equation. Okay, and let me just tell you, it's gonna be long. So this video is probably just gonna be me solving this equation. All right. So the first thing we do is you want to separate your variables, right? So here we have our dy, so we want to get dy with the dy. Remember that this right here is just a number, okay? And the k is also just a number. So the easiest way is going to be to divide both sides by y, l minus y. That way all the y's come to this side. So we get dy over dt, and if we divide, it's the same thing as saying times 1 over y, l minus y equals k. And then the last thing is I can move this dt by multiplying both sides by dt. So we get y over 1 over y times l minus y dy equals k dt. And basically now we are able to integrate both sides. Okay, this side is easy to integrate. So this side is easy. What's the integral of k? Remembering that k is just a number. So the integral of k is going to be kt and then plus c. So this is just going to come along for the ride. Really what we're going to be working on is this. Okay, I'm going to try as much as possible to remember to keep this in my equation. Just if I forget it, you know it's there. Okay, so this side we're going to use partial fractions. And basically what we are able to do is say, all right, the integral, it's already been factored out. So the integral of something over y and something over L minus y dy is equal to kt plus c. So the question here is, you pick one of the denominators, so y equals 0, and then you set it equal to 0, and in this case it's already been solved. Okay, so you take this, you cover up the y, and you plug in 0 for all the y's. So in this case it's going to be 1 over L minus 0, which we're left with 1 over L. So guess what my numerator is here? It's 1 over L. Remember that L is a constant. Okay, so keep that in mind. Alright, next up, we're going to do the same thing for the next guy. So we're going to take L minus y equals 0, solve for y, so subtract L, divide by negative, here we get negative L. Oop, sorry. Subtract L, divide by negative, you get a positive L. So we cover up the second part and we plug in L for what's left over, and you're left with a positive 1 over L. Okay? Alright, let's keep going. So now we can separate these two integrals. So we get 1 over L over y plus 1 over L minus y dy equals kt plus c. So the next step, remember that L is just a constant. So I can actually take out 1 over L. That's just the number. Okay, so I can take out 1 over L from both of these integrals. So I'm going to move up here. So I'm going to take out the 1 over L, and I'm going to be left with the integral of 1 over y. Plus, take out the 1 over L, and I'm going to be left with the integral of 1 over L minus y. Remember, this is not a coefficient here because it's with that y. Equals kt plus c. So now we remember that this is a linear denominator. So what we're left with is 1 over L times ln of the absolute value of y plus 1 over L ln of the absolute value of L minus y. Now, what is our du for L minus y? Okay, so let me ask you this on the side, kind of. Let's just move over here. If I had 4 minus y, what's my du? Okay, my du is actually going to be negative 1, right? The integral of negative y is going to be negative 1. So, don't forget that. So you're going to be multiplying by negative 1. Okay? And then this is going to equal kt plus c. So let's just clean this up. Okay? And we end up with 1 over L. There's ln of y minus, because we're multiplying by negative 1, 1 over L ln of absolute value L minus y equals kt plus c. Now we need to clean this up a lot. So the rest of this is going to be using algebra. So we've derived it. We've gotten the differential equation. Okay, we've solved the differential equation, but we do need to solve for y. So we need to get y by itself. So the rest of this is going to be algebra. Okay, so step 1, we see here that we have a 1 over L as a GCF. So I'm going to take that out. And we're left with ln of y minus ln L minus y equals kt plus c. Remember, we're trying to solve for y now. Okay, so I'm going to put that right here. Solve for y now. So we want to get y by itself, so I need to multiply both sides by L. So that way that is gone, and you're left with ln of y minus ln L minus y equals, this L gets distributed, right? Because you're multiplying this whole thing by L. So it's LKT plus LC, but remember C is just a constant, so I'm not going to write down LC because L times C is just C. It's just going to be another number C. Who cares what that number is right now? Now here we're left with the quotient property. Okay, so we are able to combine into a single logarithm. So ln of y over L minus y, all in absolute values, equals LKT plus C. We still need to get to that y. So how do I get rid of that ln? Raise it with an e, right? Both sides gets raised with an e. Alright, I'm going to need to go to the back side of this. I'll rewrite that last step. So we raised both sides with an e, and we were left with ln of y over L minus y absolute value, and then LKT plus C. Okay, so that is gone, and we're left with here with y over L minus y equals e to the LKT and e to the c. Okay, so this is e to the LKT times e to the c. Remember the power property of exponents. Okay, you can add the exponents or if they have the common base. But remember, this right here is just what? E to the c is just going to be c. Okay, e is just a number, and e raised to a random number c is just going to end up being this number c. So if we have this, we can rewrite this as y over L minus y equals a to the LKT, and then the c, I'm just going to bring it to the front. Alright, we're kind of getting there. Okay, we're kind of getting there. So now we want to get y by itself. So the one thing that I can think of doing is maybe multiplying both sides by L minus y. So that way that L minus y is gone, and we're left with y equals CE to the LKT times L minus y. So now what is the next thing that we could do that you can think of? Basically right here, this is L minus y, and it's all being multiplied by all of this. I know it seems like we're making it longer, but that's the only thing that I can think of doing right now, is distributing this to both of these. Okay, I should have done the arrows going this way. So this is y equals L C E to the LKT minus y CE to the LKT. I just distributed that CE to the LKT to L and y. And now what I can do is basically bring over the y term to this side, so I can add the y CE to the LKT to both sides. And the reason why this is going to be helpful is because I'm going to be able to factor out a y now. So this is y plus y ce to the lkt equals lce to the lkt. So now we have a common y. So this is y 1 plus ce to the lkt equals lce to the lkt. Now can I solve for y? Yes, sirree, Bob. Alright, so we divide both sides by 1 plus ce to the lkt. And now we're left with y equals lce to the lkt over 1 plus ce to the lkt. So we are pretty good over here. There is a little more that we can do to basically, we are good here, but the definition is not written this way. Okay, it is broken down a little bit more. So what I'm about to do, it's going to seem like, for what reason do we do this, but it's just the proof. It's to prove how they got the definition. Okay, so the first thing that we can do, because here's the definition. The definition says that the differential equation dy dt ky l minus y is the same as y equals, if this is a differential equation, then y equals L over 1 plus CE to the negative LKT. So I'm just going to show why that definition is right, because this does not look that way. Okay? So first thing what we could do is we can multiply both sides by 1 over C, 1 over C. And basically the reason we're trying to do that is we want to get the 1 out of the denominator and into the numerator. So if you do this, and I'm not changing the problem because 1 over c divided by 1 over c is just 1. But what this will help us do, once we multiply this here and once we distribute it to both of these guys here, we get y equals to the L. What happens to the c's? They're gone. Over 1 times 1 over c is 1 over c, and this times 1 over c is actually e to the lkt. The c's are gone. Okay? And remember, anytime you have a c, 1 over c or 3 over c, whatever it is, it's just another number that we're going to call c. C is this arbitrary number, so I don't need to worry about it being 1 over c. This is not doing anything to me. I can just rewrite it as c plus e to the lkt. But we use this to basically get rid of those c's in here and to get rid of the 1 in the denominator. Alright. Now, our definition has the 1 up top, right? So if we multiply by e to the negative lkt over e to the negative lkt, remember if you multiply exponents with the common bases, what do we do to their exponents? So if we have e to the 4 times e to the negative 4, this is the same thing as saying e to the 0, because you add those exponents, and anything raised to 0 is what? It's 1. Okay? So, here, if you multiply this by this, what you get is just L, because this will cancel out this. This will become e to the 0, which is 1. And then at the bottom, if you distribute this thing, you get c e to the negative lkt plus e to the lkt times e to the negative lkt is e to the 0 and e to the 0 is 1. And we can rewrite this, just rewrite the denominator so that it looks like the proof. So y equals L over 1 plus CE to the negative LKT. And this is our differential equation solved. So it seems like a lot, but we did use a lot of information that you need to be able to complete partial fractions and differential equations. So, how do we remember this? This is the logistic growth model. You do have to memorize the solution. Are you ever going to be asked to prove it like we just did? No, but you could be asked to do certain parts of it, okay? So how do we remember the differential equation for logistic growth? So think of lice. You see this? Lice minus licked. Lice minus licked. That's the logistic growth differential equation model. All right. And remember that this is going to be year 1. So you do have to memorize the solution. The solution to the logistic growth differential equation is y equals lice minus licked. And how you remember that that's an exponent, that's up to you, but you need to remember that that's an exponent. All right, notice the prominence of our carrying capacity value L in each form of the equation. It was there in every single part of our limit. This is very important, especially when asked for the limit at infinity, or when asked to find the y value when the y values are increasing most rapidly, i.e. the inflection value. So, do you remember when the inflection value was? Originally, we talked about it. The inflection value is going to be where L is halved. So if your carrying capacity is 1,000, then your inflection point is happening at x equals 1,000. Or y equals 1,000. Okay, so remember that your inflection point is basically where your graph is changing from concave up to concave down, and that's usually going to be happening, if this is L, this is happening at L over 2, at half of the carrying capacity. Alright, we're already at 23 minutes, so I am going to stop, but the homework, the video in the logistic growth equations section is going to be a very good starting point. If you get to it today, good. If not, we'll do these in class tomorrow. But looking at this problem, this is going to be a calculator-based problem, so bring your calculators. All right, enjoy.